I'm very pleased to welcome Professor Barbara Chapman for presenting the inaugural keynote of our workshop. She comes now from Stony Brook, where she's a professor as a professor in computer science, and the new institute that Robert Harrison has started there. I believe it's IACS. Stony Brook happens to be the place where I did my PhD, so I'm doubly pleased to welcome her. She is a leading researcher within node parallelism, Openmp at university. She came originally from New Zealand via Europe and Ireland, and the University of Houston, where she's known for having developed the Openmp compiler infrastructure. And I know how complex, thankless job it is to maintain a compiler infrastructure, but it is an invaluable tool for research on language development and so on. And so in addition to that, she has been contributing on the Openmp standard as well as OpenACC and all of these new accelerator-oriented frameworks that are coming up. And she's going to talk about directive-based parallel programming at scale, question mark. So, so hopefully she will explain the question mark as well as the title. All right, thank you, Barbara.
Okay, can you hear this? Is that right? I feel like I'm on TV or something with this thing here. In fact, that prompt, that's better, but I may have to adjust it a little bit. This prompts me to tell a horrible story, actually. It's not a good way to get started, but I can I can make us go of a schedule. So this is a horror story. So if you're a graduate student and just perhaps in the phase of going out and talking about your stuff, this is so that you know that whatever you do, you'll never be as bad as I was. So I was giving a talk as a graduate student at a conference. It was quite a big one. I was in an auditorium and I was up on the stage. And all I knew was that something was badly wrong. I didn't know what was wrong, but there was sort of a restlessness out in front of me. And of course, I'm trying to remember what I'm going to say and focus on my talk. And somebody in the front row finally got up and said, Barbara, I'm awfully sorry we can't hear you, because I had a microphone that was hanging around my neck, and they said it was banging on my belt buckle. I had a skirt with a buckle on. So anyway, so I was nervous. It's like this, right? So here I am in front of these people trying to take it off, and I had this earring on my ear, and when I was trying to take it off, this very improbably the microphone got stuck on my earring. And anyway, it got worse almost, because then I couldn't get that off, so I was trying to take my earring off, and I finally put the thing on the table, and I said, I want to talk without a microphone. And then just to make things really bad, I tripped over the microphone cable. So anyway, so I'll try not to give you any of that kind of performance today, but you know, it's the kind of thing where if you were trying to do it, it would never happen. Okay. So the talk I'm going to give is mostly about Openmp, and I really was set it out. I had two ideas in mind. One of them was, should we talk about exascale? And I said, no, I'm somewhat sleep deprived right now because of this stuff. I don't want to talk about that primarily, although it's sort of part of what's here. But I am going to talk about Openmp and the assumption that you already know something about that, and I could not resist saying a little bit about, is that working? Yes, a little bit about its history, and I'll say why in a moment. Perhaps you already know this, but anyway, it gave me an excuse to go back and think about some things I haven't thought about for a while, and it's a little bit about how Openmp got to be where it is. And I hope at the end I'm going to start talking about some of the challenges that faces, because I think we could actually learn a lot from you guys, because we started in a sort of different place, so we have different, you know, obviously different problems that we've gotten on top of, and but I think some quite tough challenges going ahead. So the prehistory of this, and I guess, you know, you always have to put a stake in the ground somewhere, and this seemed like the best place for me was actually back in an era where I wasn't programming, and probably nobody else in this room was either, and that was, in fact, the very first shared memory systems that were designed, and that was back in the 1980s when people were trying to learn or trying to build parallel machines to solve technical problems. Remember, this is sort of the early days. Is this still on? Okay. And I'm not hearing myself. It's okay. All right, good. And so people or various vendors at that stage developed some extensions to enable loop parallelism. So loops in Fortran code, C was not on the table at that time, everything was Fortran, to be executed in parallel on their different systems. And of course, as soon as that happens, what you have is code diversion. You have different features, similar but different features for different hardware out there. Not a good idea. Most of those machines were very small, so just a few processors at the time, but there were some attempts to build bigger machines, and the only reason I put this little picture in on the side here was there's one that actually had quite a large number of CPUs, but very, very slow memory, so very strong NUMA components, which, as you know, that makes it a very unforgiving machine. So there were some attempts to standardize, and again, the thing that got me thinking about all this was, do any of you know why I might be talking about PCF here? Well, it pretty much came from this university, so that was my excuse or my reason for going back and thinking about all of this. So in that time, there was huge expertise here. So again, I wasn't doing this work then either, but so we know about it from reading and from meeting some of the people later rather than being involved. But at the University of Illinois, right here in Urbana-Champaign, there were people who were both compiler experts, and obviously, like most compiler experts, we want to control everything. So everybody always wants to control everything, right? So we want to make it easy to express parallel code, and David Cook in particular, and the people who worked with him, worked very, very hard to co-design. They weren't the only people involved, but to develop something approaching a standard in this area. And it was all about parallel loops in Fortran. That was it, right? That was what you did. And the other thing that was developed at the time was this notion of parallel sections, which is, for better or worse, a somewhat static concept because you can express certain pieces of code that can be executed concurrently, but you're sort of hardwiring things in. Okay, so that actually ended up being not just something called PCF or something designed by the Parallel Computing Forum. There was actually a standards effort set up to create an official standard based on this area, but something happened. And what happened was that people discovered a different way of building machines that perform well. So it wasn't about parallelism per se. It was about trying to find something that was not only going to provide compute power, but also in a form where you could sort of see that it had potential to grow and to provide bigger systems. And that's why some of these early ones were problematic. Early shared memory machines were problematic because, again, the very numinous of them made it very hard to see how you could grow those systems and create larger ones. So this is an InMOS chip. InMOS was sort of like the cheap, inexpensive way this got started, but very shortly after people demonstrated this, there were several other companies that had built some very good custom networks that actually, again, significantly reduced the cost of non-local access, and they very quickly jumped to the top of the 500, and distributed memory parallelism was the game, and people just basically abandoned these old efforts. They were gone, right? Nobody talked about them anymore. And this became a time when people grew and grew and grew, both in terms of the applications and their use of parallel systems and in the size of the distributed memory machines themselves. And on the left, you can sort of see we actually don't think about this too much now, although, of course, we get mad when they get it wrong. But weather forecasters really started improving their weather forecasts, and it was all about the parallelism that they were able to express. And how did they do it? Well, wasn't using PCF, unfortunately, for the compiler people, right? It was also a time when people were starting to try and be more realistic and think a little bit about how to model things that weren't in rectangular grids. So weather forecasting was great. It sort of used or found ways to use rectangular grids, and by and large, but not all objects and devices in the world are square boxes, right? Okay, so did the compiler people give up on trying to make it convenient to write parallel code? Well, no, they didn't, right? And then there was the next big effort, which, how many people know about HPF? Okay, so most people, all right. I was surprised when people don't, because I think at least if you're studying compilers, it was an important effort in terms of trying to understand how to support parallel computing. But anyway, so the goal there, and in fact, I'm sorry I forgot to say this, but the connection machine had something called CM Fortran, which was also in some ways a forerunner of HPF, although not identical. It provided a high-level, so Fortran, but high-level based approach to develop essentially SIMD code. All right. So anyway, so another attempt by the compiler people primarily to try and provide a portable programming interface that would help people use these systems. In other words, let's try and provide something that gives the user convenience. And it got going in 1992, I think. Anyway, it involved a lot of people. So a huge effort. Everybody who was anybody got engaged in this effort and started trying to figure out how to make this work. How are we going to provide directives? How are we going to make it easy to program these great new, I mean, we think of them as old stuff now, but in the time they were still it was pretty new technology. Okay, so the basic idea of HPF was, sounds incredibly old-fashioned now, actually no, incredibly new, was that the data was the most important part of this. So you map the data to the machine. That was the key issue here. And then you perform the computation where the data is. Does anybody think that's important nowadays? Okay, so it's, I should have had a picture of Back to the Future here, but that was the idea of it. And so it started out with something. I was trying to remember the syntax, and I couldn't, so I must confess I kind of, anyway. But the main thing that you did was, again, there were a whole bunch of directives like the one on the top line here for mapping data. So you could map things, you could align things and map them to the system. And subroutine interfaces, still Fortran, remember, so we're not in the days of using C and C++ for technical computing, not yet. So you had to all kinds of things to do it at procedure interfaces to pass information about mappings and so on, so it was not trivial. And then the basic one was actually the parallel loop, which I just parallel do there, and I could not remember the syntax, so I didn't have it. So I was a grad student at this time, so I remember it pretty well. It was very exciting. And anyway, so we were going to, again, solve the world and solve everybody's problems and make it easy to use these machines, and well, we tried. But anyway, the big problem with HPF, I've sort of got a few other things on the next slide, but was if you have a parallel loop here, so if you think that second line, forget about the independent and put just parallel do there. What happens is that the compiler then goes in and says, well, let's have a look and see where X is. So X is on the left-hand side there. So wherever X is, that's where the computation is done. Well, if that element of array W isn't there, I'm going to have to move it. So anyway, the compiler started executing things very faithfully along this notion of do all the computation where the data is stored. That's the left-hand side, right? Later on, we tried to optimize that some. But what could happen was that if these things were not mapped in ways that were consistent, you could be moving data all around the system inside inner loops. And guess what? Communication's just not free. So it led to some... Oh, absolutely. Absolutely, that's exactly how it was done, yeah. And of course, everybody tried to optimize that later, but you still, I mean, if you didn't understand that that was what was going on, you could get a 200x slowdown with no effort whatsoever, right? It was trivial, right? I mean, no awards for that one. So yeah, so performance was very strange, actually. So if everything sort of lined up and it was, everything matched perfectly, you could get great performance, but as soon as it didn't, you tend to have communication inside the innermost loops, and it was just appalling. So there were many other things wrong with it. So there were various ways, and ended up being various different ways to express the parallelism and loops, and some companies implemented one kind, another one implemented another kind, and so you didn't even have the true ability to port your code even in terms of the actual features used. So there were many, oops, I'm sorry, I don't know what went wrong with that slide. Never mind. But anyway, so there were a lot of problems. And at the time, in fact, HPF was built on top of Fortran 90, which was a great thing because it was the appropriate thing, but Fortran 90 was also still actually a work in progress in terms of the vendors. So it was built on, it was a great idea, but it was built on stuff that was not really quite mature itself, and it was a huge leap in terms of the compiler technology needed. So compilers did not arrive soon. People were still mucking around. And then something else happened. And I'm going to jump that because we talked about that, really. MPI came out there. And MPI was, of course, very much easier to define because people had already been using communications libraries, and so they had something to build on top of. So while the compiler people were still trying to sort out all these problems and actually get something out there, MPI jumped in. It started just a little later, but it was finished much earlier because easier, right? People started implementing it, and guess what? People discovered it actually worked, and the user experiences were positive, and everything took off, and directors, I guess you could say, died a fairly horrible, painful, slow demise in the few years after that. So they got a bad rap, I'll say. Okay. And of course, that time, so with MPI becoming stable, people not only learned how to use these large systems and continually growing, so they were big in those days, was sort of like 128 processors, right? It's not the sort of scale we're talking about today, but growing. And also, this little picture on the right-hand side is reminding me to say that, too, that it also started getting used more and more in industry. So not just in the sort of rather narrow areas that had used HPC before, so aeronautics and weather forecasters, automobile industries all jumped onto using parallelism, so using HPC very early, but it became much more widely used. So MPI took off, and of course, it never looked back. Okay, so what happened then with directives? Well, shared memory came back, and in a very different way. So the start of that was really the mid to late 1990s, so it's actually also quite a long time ago now, when several of the vendors were trying to bring in or trying to provide desktop machines that had multiple CPUs. This is before multi-core, so still CPUs. And so they were small systems, and by design, not expected to be, sort of to be the big machines of the early days, or except for the distributed memory machines that were shared distributed memory that were developed primarily by SGI, or at least SGI was the company that made them successful. And they actually were very, very popular for a while, so I don't know if anybody here ever got a chance to use an Origin or an Altex, but they were actually quite successful, quite significant large-scale machines that provided global memory or globally addressable memory to the user, and so they looked like a pure shared memory machine. And compiler people who really do want, got this punch in the gut with this MPI success, they really do look for any excuse to try and make life easier for people. So they were immediately back and said, well, we know how to do something about these shared memory machines, right? We've been there before. And that was actually the start of Openmp. So Openmp was actually based very strongly on PCF, so on the stuff that came from this university. It was also driven in no small part by Cook and Associates, or still from here. So also very much involved in actually the initial design of Openmp. And that was a little bit like MPI in the sense that it was built on things that had been tried before. So HPF was this bold new leap into fairly uncharted territory at the time, and we sort of discovered the people involved in that discovered all the risks and challenges of actually doing that. This one was grounded very much on that early work on PCF and in providing parallel loops. So it's not a surprise that the very first version of Openmp in the late 1990s, where things had definitely moved on, was still very much based on Fortran and on expressing the parallelism, or expressing loop parallelism. So that was where it started. And it looked in many respects quite a bit like PCF. So in other words, nobody pretended anything but that was its origin. But it did one specific thing that was very important and quite different, and I don't think I mentioned that on the slide here. And that is, so the original The original PCF basically allowed you to express parallelism in loop nests, so you could write your loop nests one by one. This one created a concept of a parallel region, and it allowed that parallel region to actually span multiple procedures or subroutines. It was still Fortran initially. And that basically meant that you could have some concurrency. You could have directives that were what we like to call orphaned, which were in different procedures. So you could basically increase the scope of a piece of code that was going to be executed in parallel. So that was, I think, very important, not a very exciting step, but an important one for increasing the scope. And again, one thing that the directives community had learned from looking at the past successes and failures, so the people who worked on this were fairly obsessed at the time with avoiding what was seen as the mistakes made by the HPF community in terms of how they went about things and what went wrong there, and made sure that they had implementations ready pretty much when it was announced. So when Openmp was announced, it was sort of the end of 1997, and the compilers were actually there and being, you know, if you'd had Insight, I actually got use of one on an SGI machine before it was announced, but it was just before, so they actually existed, and of course a month or two later they announced these new products, so they didn't want people to be waiting for years and years while they figured out how to do it. They got their stuff done first and then announced it. So really, about 5 years after this demise of HPF, or even less actually, they were back with a different set of directives, but this time focusing on shared memory parallelism, and other than these one or two very large machines, mostly very small scale parallelism, and it was used quite successfully. So in the previous one, I actually had a slide, an illustration in the background from a code done by one of the oil companies in Houston, where I spent many years, and they used Openmp a lot because they like high-level programming, and so they did some very, very large computations using it. NASA was another place that also did a lot of work with Openmp, so they had a lot of Openmp-only codes, and of course they were running on these big machines, in that case the Origin, and showing that you could get MPI-like performance using Openmp as well. So actually worked surprisingly well on these particular machines, in part, or in no small part, I should put it that way, because SGI themselves put a huge amount of work into their system software and into supporting it. So they worked very, very hard to make it work. But the point was taken that you could actually do a good job with it, and if you were careful with how you used it, so didn't or understood what pieces of it worked well, what features didn't work so well, you could actually get MPI performance. So you could actually scale to very, very much larger than these 2 or 4 processors that were thought of as being its sweet spot at the time. Okay, couple of things that people tried to do. So looking at ways that the people tried to grow this thing. What I'm not mentioning here is expanding it to C and C++. That C part happened very, very early. C++ still has a few glitches, so it's probably a work in progress, I would say, although you can use it, but not everything works very well. Was this problem of dealing with data. So here's the big issue. So HPF focused on the data, right, and had all these directives to help you map data across your machine, and it somehow just all went horribly wrong. Shared memory, of course, is by definition shared, so why would you say anything about the data? All right. So this was the question, and this was something that people argued over in the Openmp community for many, many years, because of course we computer scientists know that data is not truly flat. But many in the Openmp communities were saying, well, you know, it is pretty flat, right? If you have 2 processes, it's probably pretty flat for most cases. If you have 4, it's probably pretty flat in most cases. If you have 1,000 or 1,024, as the SGI systems did at the time, it's actually not. So it's not surprising that there were some approaches or attempts to try and introduce various kinds of data, either direct data mappings and or affinity clauses to Openmp right from the start. So I put 1999 on this one because these were some suggestions at the time. So let's put in some data mappings, let's put in some affinity. Well, what happened with that? what happened with that was not very much. So people didn't like it. They didn't want to even look at it because most people involved in Openmp said this is not relevant to what we're doing. In other words, we don't need this. Most of them were targeting small systems. In fact, on the SGI systems, the discovery was made by most people that it was actually just as good, and this is something for coffee break if you want to find out why, just as good to use what they called a first touch mapping, which means basically that you have to, the application developer has to be a little bit careful about how they first use data, because the first processor that touches it, or it will be stored as close as possible to that. So you can actually use that to essentially implicitly map your data out across the machine. And if you do that, then things actually went well. So SGI actually, again, partly because they had a good implementation, to discovered they could get away with that. So people suggested having data mappings then, which sounds very modern now, but it died out because, in fact, the only really big machine that needed it had another approach that worked. There were some other attempts at the time. There were, in fact, a whole bunch of them, so this is just one representative one, to try and get Openmp to work across clusters. And a whole bunch of different approaches taken to try and do that too. As you probably noticed, there is no Openmp, or is no commercial product using it, so it tells you that that didn't work out. There are some features that are very, very hard to deal with, and in fact it turns out that if you have, because Openmp can have sequential parts in its code, doing a good job of those starts to become a real problem. So there are some inherent problems. Doesn't mean that it could never work, but certainly it didn't work particularly well. Anyway, so what happened next? I'm sorry, a few of these slides are not looking the way they used to, so I'm not sure why that's happening. Okay. We'll have to just live with it. I'm sorry, I can't do much about it now. So something that you know very well, of course, was the notion of tasks. In other words, being pieces of work that have some associated data that are generated and will be executed at some time. So the Openmp community actually introduced tasks in a no small part because they were trying to capture a much bigger audience. So I left out a slide that I probably should have put back in here, and it's just saying that multi-core came out. So Openmp, before the days of multi-core processing, and before people said that, Intel in particular said this is the way the world's going, I won't say it was a backwater. It was more than a backwater, but it wasn't mainstream. It wasn't that important in the scope of things. So there were a group of people who worked on it. It was all somewhat slow because the vendors didn't put a lot of effort into it. So these things all have their reasons. All of a sudden, it was very clear that multi-core was going to be mainstream, and we needed some approaches to programming multi-core systems that were not too low level. Or at least there was a perceived need for it, I'll put it that way. And so all of a sudden, the vendors put a lot more money into it. There were more people coming. We had to start. So as one of the people who'd been quite a lot involved in it, it was very annoying, of course, for a while, because we had to go back and rehash stuff that we'd talked about years before, but it's what happens then. But it really took off because of multi-core, and because people saw that this was something that they felt had to be a part of the programming landscape. And then the fact that it was based on primarily on allowing you to say how loops were going to be parallelized became rather limiting. So tasks, in fact, to say it actually didn't make the standard until 2008, didn't become official. People have been working on it for several years, partly because going back and looking at some of the existing tasking features and not liking them as much in the form that they were in, and sort of took a lot more time to try and figure out how this would fit into Openmp. But it was a big divergence. This was no longer PCF, right? So until that time, you could argue that it was still really PCF with some additions and extensions, but then it suddenly wasn't. And the way that this happens in Openmp is a lot more constrained, because Openmp has these, what I call synchronization points, if you like, barriers that are introduced in various places, in particular at the end of parallel regions. And so tasks in this model are all created when they're created, so when it's written in the code, and will be executed before the next barrier. So at that point, they have to all be done, and then you can go on and do something else and maybe create more tasks and execute them. And they had to be all completely independent. So create a bunch of things, do it, and come back. So a little bit limited, but still compared to what was there before, quite powerful, and allowed you to also, in particular, parallelize loop nests that weren't sort of countable loops in a technical sense. And then the next thing that, of course, happened was that a lot of people, some people, wanted to make this more expressive. And again, it was at the time it was less about high performance and about the things we talk about today, and more about trying to capture more codes, because the focus at this time was very much on small-scale parallelism. Right? It wasn't on the big machines at all. And so there were various efforts. Sorry, if you could read this slide properly, which we can't, it would have showed you something that we were doing in our group, which was not the way that actually that the standard went. So it was kind of close, but there were various efforts to try and think about how to express tasks that had dependencies between them and allow them to be executed. And of course, as every healthy area of research, minor divergences of opinion, all with different pros and cons. So again, ours didn't work, but we focused a lot on our implementation and on, sort of trying to make it very efficient. And this was a grad student's work, actually, this particular case, and a sort of low is good. So performance, the versions that she worked with our compiler, she was showing that we got great performance, but unfortunately, in terms of expressivity, our part wasn't so good. So in terms of the actual feature set, it didn't work out, but she was did some very good runtime work, actually, in trying to get them to work. Anyway, we now have tasks. I'm sorry, I should have left that slide up for a little longer. So we now have tasks in Openmp. They can have dependencies between them, and we have some synchronization. We still have this somewhat stylized fashion of writing things, I would say, because, again, we have barriers at different places, so you have to execute the tasks before you hit a barrier, and then you go on and create more. So it's not a fully asynchronous mode. It's a sort of a somewhat restricted form, which probably is good in many cases. It's possibly also easier to reason about, but doesn't involve the full asynchrony of other models. Okay, but we weren't able to rest on our laurels there anyway, because the next big thing happened, and that was heterogeneity. So as people discovered, in part, I think just a price performance thing, back of the envelope calculation, that you could get more bang for your buck, so to speak, by configuring accelerators, and because they became a little easier to use, we discovered that some of the bigger systems were getting accelerators. So we had HPC users here too, because we had multi-core on the nodes, but not so many. Right? At that time, I remember going to Oak Ridge one time and giving a talk, and they came and listened to me and said thank you and went back to their desks, but they weren't really using Openmp, so that wasn't its market at all. However, I met a lot of people using it in databases and all kinds of different areas. So there was a user base, but it wasn't really HPC. They were sort of politely interested for the large part, but not doing too much with it. Okay, that changed a whole bunch as soon as heterogeneous cores were configured, and mostly GPU accelerators, of course. And that actually set off this huge discussion inside the Openmp community about what, if anything, to do about this whole new technology that was being used, because, of course, GPUs, or at least NVIDIA, wasn't the only company developing them, and certainly they were most of the ones being actually deployed, but wasn't the only show in town. And that was kind of interesting, because Openmp started with this premise of keep things as simple as you possibly can. And these accelerators were accelerator cards were connected via PCI Express, so they did not, and they still today mostly don't have shared memory. So people say, well, isn't Openmp about shared memory, and isn't it supposed to be simple? Another aspect, of course, was that there were plenty of companies involved in Openmp that were not planning to deploy accelerators, and they weren't terribly interested. So the bottom line is that for a while, Openmp, or at least the mainstream opinion, was that we don't go there. So we're not going to look at this. And we know what happened then. We suddenly got something which I think many of them perceive as being a competitor, although at the time they arguably weren't, because they were moving into a space that was being ignored, and quite deliberately ignored by most of Openmp, or most people. And so the story's a little more complicated than I'm saying there now, but anyway, that's the short version. So OpenACC was, of course, driven primarily by NVIDIA to try and provide directives for use on their accelerator cards in conjunction with CPU hosts. And it looked a lot like Openmp in terms of the way they describe things. Oops. But was very focused. So it was focused. They also set up an effort which, and we joined it too because we very much believe in standardization. And we'd actually been exploring in my group for several years, sort of trying to understand what we needed to do at that level and try to understand the problems and how one might be able to go about it. We had been doing that in the expectation that it would actually be added to Openmp, but that was something that hadn't been happening. And or it was being explored, but hadn't really happened. And so the idea here is, again, to be able to express parallelism in loops that are going to be accelerated. And of course, since the architecture is somewhat different, it had a slightly different flavor to it. But you need a little bit more than that. So I'm going to go on. I'm going to watch my time here, so I'll say this rather quickly. Sort of jumping to some things that I think are still works in progress. Okay, don't worry about it. Okay, I'll try not to be too. You don't want to give me too much. I have the professorial problem that I can talk for a long time, so you don't want to do that. Okay. Anyway, so OpenACC is still with us, and has anybody used it here? No, so you don't do this. Okay, that's fine. So OpenACC is designed to run on accelerators, so that's not just NVIDIA GPUs, also AMD's APUs. Although I'd say just because of the kinds of systems that are out there, it's probably 90% NVIDIA usage today. And so the user can say a little bit more about how to parallelize, or have additional levels of parallelism in loop nests, and there's another piece that I'm going to defer to another slide. But one of the things that we discovered is that it's kind of difficult, even with the information that the user gives, so this is today, to actually come up with a good compiler strategy for implementing those loop nests, because you typically have an additional level of parallelism that the compiler needs to determine. And the correct or the most useful choice of that is a bit elusive. So in other words, different choices can be appropriate on different kernels. And I actually have someone who's doing his PhD still on this, so he's still wrapping it up. And interestingly enough, so the reason for this is not, it's a bit complicated, right? Because when you spread things out, you can get different numbers of threads. They can have different register usage, but also different data access patterns. And so the user is not saying, and thankfully, thank heavens, not having to say too much about how the data is mapped to the different memories on the GPUs, but the different translation patterns have different implications for that. And what my PhD student is telling me, he said the most important indicator for the choice of translation of the loop nest is the data reuse pattern. And which I found kind of interesting, because we first started looking at these and I said, well, I can see a pretty picture here just like you can, but I can't make any sense out of that, and that's of course always a bit of a challenge. So I'd say we're still actually learning to do a good job on that, and it's not that things are really bad, but I think I think this is very doable, but we're still getting there. So what happened? Well, okay, so OpenACC was a much smaller effort. It was doing one thing and went off. It had a mission, started really working very hard on that. There were several compilers out there, and Openmp suddenly looked up and said, oops, we have some other directives there. This is not good. This is not good for the user, right? So you don't really, if you're trying to use directives, you don't want to have two different sets in the same code. It's not nice, right? So maybe we really better do something here. And sorry, this slide's gotten really screwed up too. So anyway, I'll see what I can do. Okay, so you can see one line that really matters. That's good. So there should be some other code there. So Openmp actually had some, so this is kind of hard to describe, but the people working on OpenACC and the people working on Openmp were often the same people, right? They weren't just the same companies, they were the same people. So it's not really a surprise that they're similar. The thing that's a surprise is that they're not identical, right? And they probably should have been, but they're not. They're similar but not identical. And so what Openmp does is allows you to specify, and this is this pragma line that you are seeing there, a region of code that is going to be executed on an accelerated device. And so you have to insert that in your code. And the other thing that it does, and this actually is, there is a one-to-one mapping between these still in Openmp and OpenACC, so it was the OpenACC people who really defined these, is you actually have something also called a data region. And the reason for that is that especially on today's machines, you have to be very careful with the way the data is both sent, or when and where it's sent to the device, and how long it's there. Right? So in other words, because it's expensive to transfer the data and there isn't a lot of memory on it, you have to be very, very judicious. And the results that people were seeing was that basically if the user doesn't say this, you're not going to get good performance. Right? So you have to allow the user to do it. And having these things separated out made it possible, for example, for data to have a much longer lifetime than any particular kernel that was going to be executed on it. So put some of the data there and leave it there for a while. And in the best possible case, you'll be running a bunch of different kernels with the same data, and then you can release it and send it off. Yeah. Yes. Yeah. Yeah. So for the accelerators themselves? Okay. Mhm. Yes. Yeah. Uh, becomes CUDA code? Can do, yeah. So our compiler, for example, we translate it to PTX actually, so we go to the low level for NVIDIA if we know we're doing that, but we can also translate it to OpenCL. So there are a bunch of different ways you could implement this in practice. So it doesn't have to be at that level, it can be at a lower level. Yeah. That's a good question. Yes, usually there is. Yeah, if that's what you know that your target is. Yeah, yeah, yeah. Okay. So I thought you were asking why would the user do this, and that's a whole different question. And we could come back and talk about that too if you want. Yeah. So, yeah, yeah, yeah. Correct. Yeah. Mm. Okay. Yep. Sure.
Don't you have to specify the chunk size, or is that just come because it's a G, or is it magic?
That's a very good question. Yeah. So you don't have to, no. So at least so there's a couple of things. I'm sorry, I can't talk about the code that's there because for some reason it's not displaying properly, but there's behind the scenes, if you want to use these, and this has completely irrelevant whether it's Openmp or OpenACC, the application developer has to, in fact, be sure that the kernel size is appropriate. So you could end up doing a lot of reworking of your code to get this to work right. There's not a free lunch here, right? So in other words, it's about not so much the computation, but about the way you're using your data. So really, you need to reorganize it to reuse data as much as possible while it's on the device, and then move it off. And if your code wasn't written that way, there can be a lot of work involved. But the reason I said that's a great question is that actually we had an interesting epiphany. This is very early work, so I'm not going to try and explain these graphs particularly well, but we had a very early version of the Openmp translation for accelerators. So these are still, I think, still maturing. There are some of them out there, but it was in part, I think, because people didn't want to release things until they were getting good performance, and I think there are a lot of issues, and there were some of the same issues that we were seeing in OpenACC that were coming up and making it hard to actually do a good job on the translation. So what we were seeing was the code that was here actually has a loop nest in it, And we discovered that on the Openmp, you can create a schedule and you can specify chunk size and other things. And depending on what you chose there for that schedule, so that's actually really the mapping of iterations to the threads, you could get very different performance, right? Which is kind of weird, right? But I mean, really different performance. Why? Same reason as at OpenACC, that when you do that, what you're really doing, what's going to happen under the hoods is that you're going to get different data access patterns, and your data will probably be laid out differently in memory. So it's not just in quote marks about the actual iterations or the iteration numbers or anything like that. So there's a kind of a good and a bad thing in that, and in the sense that I think this is one of the things with maturity that we have to learn to handle better, but the other side is that it's very easy to experiment with different things because you're just changing that clause and you can sort of have a look and figure out what works best for your code. But it's not the way you really want things to be. So which is why I'm kind of calling this work in progress, because I think we're still getting on top of this issue. And it's all about the implications for data mapping. The other thing that's still I would say under construction. I shamelessly stole this particular image, and that's this problem of what people are calling deep copy nowadays. So in other words, when you're transferring data to and from the accelerator card, you have to be very careful. You want both because of the cost of the transfer, at least that's today, but also because you have limited device memory, you want to be able to transfer exactly the data that you need and not large data structures. But you also really don't want people to have to rewrite their code to actually make that happen. And there's a lot of rewriting that's being done right now to try and ensure that only the parts of, if you have a complex data structure, that you're only transferring the parts over that you really need. So people are trying to think about how to make this easier. So in other words, how can we make it possible and efficient for people to transfer over precisely the data that they want to transfer and not everything else? A simple problem, but it's not so easy to actually provide something that's easy to use as a feature. So it's so there are still problems with data is the other one. Something I had to put in just partly because of the audience here. I'm so sorry, you're not seeing my points. Was about adapting the program, so I'll just talk about what should be on the slide. So this is something that we actually been looking at for quite a while, is how to adapt an Openmp program while it's executing. And the way that's easy to do in Openmp is very different from things that you would look at because we have different primitives and very structured code, essentially. But the thing that's kind of interesting, or the interesting opportunity in Openmp, is the fact that when the compiler translates Openmp, it ends up with runtime code where usually library routines inserted by the compiler are actually starting threads, stopping them, or putting them to sleep, waking them up, giving them work, or telling them how to go and figure out their work, right? So in a sense, so they're kind of orchestrating things. And these because they've been inserted by the compiler, the implementation actually knows about it, right? And that means that you can also have multiple versions of them. So you could have a version of something that starts up a parallel region, but you could have another version that says start up the parallel region and collect this kind of information for me while you're doing it. And so you can use this to collect hardware counter information in particular at very low cost and to turn that on and off. And so we've been doing that for quite a while to actually look at how we can gather runtime information with very low overheads and potentially use it. There are other ways that Openmp can be adaptive too. So we learned at some point, I had a great student who did this work and then disappeared, unfortunately. He went back to India and disappeared on me. We were looking at adapting, for example, the barrier routines and especially the different kinds of synchronization. So we had a whole bunch of different implementations and chose them depending on the context. And so lots of ways in which you could get sort of what I call the low-hanging fruit here in terms of ways that you can adjust its execution without much overhead. And I think that latter part is very important. So one thing we looked at in particular, this is really old work, so I'm going to just hint at it, or just say it very, very quickly right now. Has anybody written an Openmp program that worked really badly? Okay. All right. My very first one was so bad I won't confess, except to tell you it was really, really bad. Anyway, it's easy, unfortunately, and there are one or two things that make it easy to do it badly and inadvertently, even if you're very smart. And one of the worst of them is this false sharing, where data basically, it's not a bug because you have different threads accessing different data, but they're on the same cache line, and so the cache line's ping-ponging around. The degradation can be very severe. And it's kind of hard to notice. I mean, it's hard to explain to someone who's an application developer and not a computer scientist what's going on without trying to come up with all this, stuff and, waving your hands and so on. So anyway, one of our dreams was to be able to figure this out and fix it automatically. And again, this is old work. And for various reasons, one of the many things I've walked on from and haven't gone back to, but I should. So I had a very smart master's student who figured out that again, he could very easily detect that false sharing was happening or something that had the same properties. And if you're getting these many cache invalidations, you have a problem no matter where it is. But it's pretty much false sharing. And he was looking at, I'm sorry for the context here, he's looking at this using a benchmark suite where he did not introduce any problems. He just picked it up to see what happened and discovered that this particular benchmark was full of false sharing, so quite obviously inadvertently. And not only discovered that, he could also, rather expensively with heap data, but other than that, could also fairly well identify not just that it was occurring and where it was occurring, but which data objects were causing it. So plenty of information. And showed how much faster these particular benchmarks were once that had been fixed. So the next thing that we want to do is, of course, do this automatically. And that's where things started to get hairy because, in fact, an automatic fix it really involves rewriting the code. So I had somebody who did a rather nice PhD looking at that problem, and we discovered there were some kinds where you could, in fact, choose a different strategy if you knew that this was a problem. And do something, so there's a potential for a cycle, but there was some where it was eluding us. So I would say we sort of got part of the way there. It's another of the many things where I really wish we could pick that up again and really solve this problem, because if we could do that dynamically and actually fix these things for people, then I think there would be many much better performance experiences. Okay, some other work that's actually ongoing, because even I knew I was going to run out of time, I didn't put any more than this, was trying to help people manage energy. So obviously power and energy are big deals today if you're using HPC. And I would say, for me, I sort of probably look like a deer caught in the headlights if someone said to me, rewrite your code to reduce your power consumption. I wouldn't know how to do that, right? It turns out that actually Openmp has various policies, so related, again, especially to how loop nests are executed, and that tweaking those and tweaking the numbers of threads in your team can make quite a big difference to the amount of power and energy used, so energy really. And so we're looking at different ways to try and put that into a system to help tweak those things, possibly even adaptively and possibly even transparently. So that's some work in progress that would be, I think, pretty cool, because in contrast to the false sharing, those are all adjustments that we know how to make, and we don't need the user to make them. So that gives me some cause for hope that we can actually transparently make adjustments there that will be good ones. Okay, so I'm going to try and I'll wrap up fairly quickly. I think you know some of these things. So Openmp has gone through all kinds of evolutions. So it's been something that started out as purely for technical computing in the 1980s. Then it was reincarnated as something for desktops, and actually had main use outside of HPC for some years. Then when multi-core became important, it became much more important to provide much broader expressivity, so it wasn't just about loops anymore. And now we're in a very different mode again because of petascale, exascale, large-scale computing. And not just because of that, but because of the way the nodes are being configured, right? So we don't just have multi-core now, but arguably many-core on a lot of systems. They're complex. The core count is growing. They're becoming more complex in every kind of a way. And according to recent data, I've seen almost all of the DOE codes now, or if they're MPI-based ones, they also already have Openmp and or OpenACC in them, sometimes both. So people are starting to really try and use it, and I probably should have put a slide on this, but that has been accompanied by let's say, I was going to not resurgence, but a surge of interest from the labs, and so almost all of the DOE labs are also actually active members at this point. So they all joined the Openmp Standards Committee, which is an official organization, has companies or organizations join, not individuals, and at some point became as ponderous as any other standards committee because of the number of people and the number of interests on it. So which also became a bit of a problem because obviously if things are changing around you so much, you need to be able to respond to them. So I think in last few years, they've done a fairly good job on the latter and at least speeding things up a little. But of course, change is ongoing, and we don't just have many, many more cores coming. We don't just have heterogeneous cores. We have new kinds of memory coming. We're going to have many more, I think, challenges related to memory architectures, scratch memory, and so on. And of course, the accelerators themselves, which I think are very much part of our landscape, are also being not only well, they are changing too, but the method of integration is changing, and hopefully going to be a little bit more forgiving, so at least in terms of the overall cost. So in that context, it's kind of interesting because Openmp has to figure out where it is in this whole landscape of exascale programming that I managed to avoid not talking about until now, but of course as everybody is expecting the next wave, the next generation or two generations of computer hardware to come, and that scope, everybody is expecting that the primary growth, again, will be inside the node, and that's where our sweet spot is, right? And so the question that some of us have is, what is going to be needed for Openmp to stay relevant and to be useful? So once you have a big user base, you also have obligations, right? So I need to try and do that. And one of the things that Openmp has arguably always had in terms of people or sort of terms of things that people have seen around for a long time is this familiarity thing. So one of the things that we hear is that people are comfortable with Openmp in terms of just recognizing, understanding what the directives mean and essentially what they do. I would distinguish that from being able to use them well, because I've seen some absolutely dreadful Openmp code, right? So there's this notion among some people that I hope no Charm++ user would ever dream of, is that you have some directives. So here's my code. Okay, here's some directives. Let's throw 3 of them in and everything's going to work perfectly. And of course, life is not like that. You actually have to think about them and sometimes adapt your code to make them work well. And so some of it's pretty bad. But anyway, so it's trying to position itself as a medium-level standard, but there are some things that are going to be interesting, and I'm going to wrap up with just a couple of slides on this, things that we have to think about. So this is, again, so I know about your keynote tomorrow is going to be obviously in this vein, so it'll be interesting. We've had this environment for a long time where the Openmp implementation was king, right? So, so the Openmp implementation creates these runtime things. We could do some nice adaptation because we knew what was going on and we controlled everything within our realm. If you have a system with Openmp on each node, running code, they don't talk to each other. They're all doing their own thing, so they're not moving data around or not moving work around between them. So a very controlled world, and really, right? But it worked well. So if we get a very different kind of a beast, and we have to be able to target different kinds of runtime systems, then we have a lot of questions that we have to answer. And one of the things that we've been doing, and again, I'm not going to say very much about this because you're getting the keynote tomorrow, but as we've been looking at what happens if you translate something like Openmp onto HPX, which is again, designed to be a global system and offers low-level tasks, or OCR, Open Common Runtime, which has been designed by a bunch of actors, including Intel, and also is based on this notion of having, or actually really, I'll just use the word tasks, and passing data between them, and no such notion as global data. So Openmp has this shared data, right? And the tasks or the threads are sharing them, and they have a very different world where things are being passed from one to another, and you don't have the shared context, and in particular, you don't have threads. So very, very different. And yeah, so we discovered that you can do it, but it's not easy, right? So Openmp has threads. Threads have a lot of benefits. It turns out because they have their own stack, you can do a lot of things that actually become very efficient with data when you have threads. And now we have to translate this to a world that doesn't know about them and possibly doesn't have any concept of data that can be sort of in the environment rather than explicitly passed. So some of the features. So the good news is that you can actually do it. The problem that we had was, so I'm sorry, this total mess here. So this is ongoing work, so I never set too much store by figures like this, but and I'm not even, okay, so this was HPX native code with its native, again, I'll just call everything tasks in this talk. This one, actually, this was done, it says Intel, but it was a version we were using Intel ABI, so for the output that we had. So this was essentially Openmp code that had been translated just as it was to HPX, and it executed really, really well, but as you can see, it sort of tails off. So we had a lot of trouble getting, or still having trouble getting good performance in this mode because it's a very different beast, right? So, and we have found that the benefits that we have in our own environment, particularly with the way that we access data, are lost in this context. So it's not that you can't do it, but it's a somewhat uneasy fit. They are really very different. And so it's interesting challenges going ahead. Something that we did years and years and years ago, on this one actually is working perfectly, that's odd. Okay, so this is actually, if you probably see the bottom, this is from a publication in 2002, so that's how old this was. We were actually looking at Openmp. So this is left-hand side is supposed to be sort of showing you how Openmp executes. So you've got a bunch of chunks, and then there's a barrier, and then the next set, and then so on. So it's sort of this very stylized execution. And in our compiler, we analyzed, this was actually taken from a piece of real code, so this was nothing, it was a very straightforward DOE application code. So this is something that very much does exist in real applications. And this was actually analyzing just these same chunks and trying to identify where there really were dependencies between them, right? And so these are, you could think of them as tasks again, I suppose. We didn't think of them that way at the time, but they are little units of work. And this was the actual graph, and we translated Openmp, so no tasks in Openmp at that time. So this was very simple days. But we translated Openmp to this collection of little work units, and we used a runtime system that had been developed at Los Alamos to actually execute them, and found that actually worked quite well. We had an interesting experience, and I hope to hear from some of your work on this actually, because one thing that we discovered was that to get really good results, we did need to know about the data usage. And so what we ended up doing at the time was having the compiler analyze the data usage and do a best effort to tell the runtime that certain chunks should be executed on the same resource. In other words, wild and total complete load balancing, at least in that experiment, was not the right way to go. You needed to take the data usage very much into account, but it worked. And so it's another thing where I kind of wish we'd done more. Anyway, I'm going to finish on that, but just say, I'll just skip this one. So, oh, I was fully expecting this slide not to display, so okay. So it's a funny thing, so we seem to go in a lot of cycles. The slide I just skipped over was going to say that one of the big things that's dominating our minds right now is again, going back to data, right? So what do we need to say? What kinds of affinity do we need? What about all the problems that you can run into if you're trying to target different machines, in particular with accelerators, so possibly dealing with small memories and transfer times, how to get this accuracy in data and how to do all of that while you're not completely hardwiring everything into the code, right? And so what I want to finish up with was something that I think for us is a problem, and it's where you kind of started, right? So Openmp, just really this one. So this is, I think this is the big problem that Openmp has now, or the challenge. I think it's positive, it's a challenge, right? But we have to figure out what to do about this, and I don't think we've addressed it at this point. And that is that Openmp has sort of, in order to allow people to get really good performance, it allows you to say not just how you want not just that you want a loop to execute in parallel, but how you want the chunks to be mapped out to the threads, and it can allow you to say things about how to place the threads on your hardware. It's becoming, if anything, more hardwired, right? So I can get great performance by specifying all these things and by figuring out what works well on my machine. When you go to another machine, you have to change some of those details, presumably, right? It's good in one sense if that's the target you want. It's usually a finite. I mean, it's not a lot of stuff that you have to change unless there's a really big difference in the architectures, and that's where things become hard. So with this, particular with this emphasis that's coming down again from the HPC community now. So remember, Openmp for a long time was not HPC relevant, not really, right? And it became that. With this demand that people need to be able to use not just the same programming model, but the same code to run on some very different machines, we now have systems that really emphasize SIMD parallelism and ones that don't. And we probably have rather different requirements in terms of the way that the data is managed. And unfortunately, unfortunately in this context, Openmp has sort of opted to be not prescriptive, which is what everybody wanted it to be at the time. So when in the first defined, people said we want people, HPF this was very much a sort of a blowback from HPF not working from those early days. People need to be able to understand the performance, right? They're going to write the code. We don't need them to go away and take, even if it's a great compiler class, they're probably not going to show up. So they need to be able to understand this without knowing all the details of the compilation, right? So the performance has to be transparent. Okay, that means you've got to be prescriptive, right? So in other words, execute everything exactly the way the user told you to. Right. So that was an absolute must at the time, and it's kind of coming back to hit us right now because to say, okay, the compiler does exactly what you tell it to do, right? No scope, and to get performance, you probably put a lot of stuff in there that's going to suit this particular target machine. But now people are telling us that they really want the same code to work on really different architectures. This doesn't work. Okay, so there's a real challenge there, and I don't know what Openmp is going to do about this. I know that they're going to be confronted with it because there are a lot of DOE people who are very engaged in it right now. So, going to have to go away and think about it. And I think so. If my 2 cents, I have an idea of what I would like to try, but again, it's kind of where we're at. Okay, well, thank you for letting me go shamelessly over time because I think I took even more than that time. So. I told you shouldn't have said that.
Thank you very much.
Thank you.
All right, time for a couple of questions. The only thing that happens is we postpone more than a couple of questions.
Absolutely, yeah. Sure. Mm-hmm. Yes. That's a great question, and I wish we could sort of say that. A lot of people think, so it's actually 4.5 now because they were, Openmp, the community was trying very hard to do just that, and sort of, I hope for the right reasons. But there are actually 1 or 2 features in OpenACC that still don't work in Openmp. I personally expect that as soon as Openmp compilers are demonstrating the same kinds of performance. In other words, they're sort of getting there, but they're not quite there. I think that will just de facto happen. There are still some people who argue that OpenACC needs to be around for a while because they're so focused and faster moving. That's also correct. But again, in terms of using a code, the more interfaces you have, the messier it becomes. So I think as soon as people start seeing that, they can. The good thing is that for some parts of it, the translation from one to the other is actually very easy. So again, they weren't really developed in total isolation, so it's not a surprise. Yeah. Thanks. Yeah.
So one thing that I've seen and heard people say about like the accelerator work in Openmp is
Mm-hmm.
that it's kind of cramming in various vendors' independent extensions in ways that don't necessarily make sense on each other's hardware. That it's not
Yeah.
a
Yeah.
common approach that would be portable. It's just a standardized way of acting over different things. Do you see that converging or?
So especially specifically for the accelerators? I don't really think that's correct. And in fact, it's not too different from OpenACC, which tells you then, which I think arguably people would say was the opposite. So I think it's difficult right now because what I don't like about the interface that we have is it's kind of kludgy. And of course, there's a big difference. If you wanted something to maybe run on an accelerator, maybe on the host, they kind of look different. I don't like those things about it at all. A lot of that was motivated by the very high cost of transferring data. So I think, and again, that's not a done deal. There is still a lot of stuff on the table that's basically related to trying to find implicit, user-friendly, if I can use that word, ways to influence the way the memory is being laid out, which is motivated by the things I tried to hint at there with the loop optimizations. So it's not quite done yet. I would love to see something that's smoother personally, but I don't think it was motivated by different people. There was definitely a lot of politics going into it. I think there was an effort to try and be fairly broad because we actually have embedded users in the embedded space and other things too, and very different kinds of memory hierarchies, different kinds of subsystems. So it was difficult in that sense, but I don't think it was. I don't think it was a matter of different people cramming stuff in. I wouldn't characterize it that way, but it's a bit messy. Yeah, I agree with that. Yes. Yeah.
One last
Oh,
question
okay.
from me.
Oh, okay.
So
Yeah.
we work a lot on what we call persistence, or
Mhm.
principle of persistence. We rely on that a lot.
Mhm.
In Openmp terms, it is basically from outer iteration to outer iteration, subsequent outer iterations. The behavior is similar.
Mhm.
Be able to learn from that and schedule
I see.
the next iteration differently.
Right.
How I would apply that idea to Openmp. Is there some effort in that direction of yours?
Not that I'm aware of, not really. We tried to do that in some earlier work where we were trying to decide which barrier routines, for example, to use or which synchronization constructs, and you could apply that to some extent, and that was easy to do because it was all hidden in the runtime and it was very low cost. So, yeah, but as a principle, I don't. If people are doing it, I'm not aware of it. They might be in the same kind of a vein, but not in a bigger sense. Yeah.
All right.
Thank you.
Thanks again.
Thank you.